So we're going to start by looking at this theorem, the solution of homogeneous system equation parameters. And what we have is we have n is less than k, and we have a homogeneous system with k variables and n equations. We'd like to say it has a non-trivial solution. And the idea here is, given k variables, let f be the free variables and b be the basic variables. Then k is going to equal f plus b. Okay. Now, each equation can produce at most one basic variable. So there are at most n basic variables. As k is greater than n, f is greater than 0. Thus, our solution vector has at least one free variable. Letting this variable equal 1 gives a non-trivial solution. And we have our proof. So we have at least one non-trivial solution. Wonderful. So what does this mean in terms of linear dependence, linear independence? How could we use this? Well, if we have n equations and we have more than n variables left, that means, and it's a system of equations equaling to 0, it means we have at least one non-trivial linear combination of our k vectors that give us the 0 solution, or we have a dependent set. There's linear dependency within the set. So now that we've dealt with the homogeneous, we're going to look at our non-homogeneous. And our non-homogeneous, we're really just changing one thing. This vector here is not all 0. Okay? And our process for solving non-homogeneous system of equations is extremely similar. What we're going to do is we're going to create our augmented matrix. We're going to convert to echelon form. Then once we have our echelon form, we're going to do everything that we would normally do for our homogeneous system of equations. And we're going to replace b prime with 0. And we're going to solve for what the homogeneous solution would be using our echelon form matrix. Then, once we have our solution for our homogeneous system of equations, we're going to solve for our particular. And once we have our particular, we're going to take our particular plus any vector from our solution space for our homogeneous system of equations, and that sum creates an affine set, which is our solution. And the set of the following form is an affine set. What an affine set is if I have, let's say, a line will form a subspace. But if I add a vector to every entry of the line, and I shift that line up everywhere, this line I create that line is not a subspace. It's an affine set. It's a subspace that has been shifted. Okay. And we'll discuss these in more detail, and you'll discuss affine sets, and you'll use them in terms of projections and everything, and best approximations, much more in B24. But for now, what we're looking at is the affine sets form a solution. What it is it's a subspace SH, which is our homogeneous portion, plus the set containing our particular solution. And we take the sum of those sets, and that gives us our affine set, which is our solution set for the particular. Now that we have the particular, we're solving for a single vector. And in the particular solution, we could have no valid vector, or we could have a valid vector. So now, with the idea of solving for your homogeneous or your particular solution, we can have no solution. That is, XP does not exist. And this is our inconsistent systems of equations. Now, one solution, our particular exists, and our solutions, our set of homogeneous solutions is equal to just the zero vector. And for an infinite number of solutions, XP exists and SH contains at least one non-zero solution. Now that we've reviewed the process, we're going to apply this process to a few problems. The first process that we're going to apply it to is we're going to apply it to this matrix here. Now, this matrix here that we have, 1, minus 1, 0, 1, 1, 1, 1, 1, 2, 3, 0, 2. And I'm going to start by taking R2 minus R1, replacing R2. And if we remember our process, we start by selecting my pivot. I have my pivot, make it 1. Once it's 1, put it in the right spot. Once it's in the right spot, 0 out the other column entries. 1, minus 1, 0, 1, 0, 1, 1, 0, 2, 3, 0, 2. R3 minus 2R1, replacing R3, gives the set 1, minus 1, 0, 1, 0, 1, 1, 0, 0, 5, 0, 0. We take R1, we add R2 to it, because this is going to be my next pivot entry. I've made it 1, put it in the right spot. And now I get 1, 0, 1, 1, 0, 1, 1, 0, 0, 5, 0, 0. My next operation is row 3 minus 5, row 2 replaces row 3. And this gives me the set 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, minus 5, 0. Now I can take row 5. I'm going to do 1 over minus 5 times row 3 to replace row 3, giving me 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0. And if we continue for a little bit, and we're just going to pretend like this doesn't exist. We apply R2, R1 minus R3 replaces R1, and R2 minus R3 replaces R2, and we get 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. And now from here, we have our augmented matrix, and it's in echelon form. So now that I have it in echelon form, I'm going to do 2 steps. First is solve the homogeneous solution. So I'm going to start by let x be in SH. And what is my system of equations? My system of equations, this gives me x1 equals 0, x2 equals 0, x3 equals 0. What are my basic variables? My basic variables are x1, x2, and x3 using pivot entries. And my free variables, well, they're whatever aren't basic, but all of my variables are basic, so I have none. And now, as x is in SH, x equals x1, x2, x3. And I let my free variables be free, but I have none, so I'm done. So now I use the system equations to set what my basic variables are. x1 equals 0, x2 equals 0, and x3 equals 0. This gives me that SH, that V equals the 0 vector, and SH equals the span of the 0 vector. But now, what about my particular solution?